you to my lecture today. Of course, I know you will be surprised with the title that I want to present today. The essence of this title is as a result of the feedback that I got. I am a professor who actually cherishes feedbacks a lot. And that is the reason why I decided to slow down and to have a recap on what we've done before. And particularly, what I'm going to be reviewing today, of course, are the areas that will be covered in the midterm too. And I'm also going to give a tip on assignment 6. The PCA example that I reserved for today before I've been shifted to next week. Of course, if you look at the syllabus suggests we're still going to have PCA up to next week, Monday. All what I require from you at this point is to sit back, listen, and answer questions where necessary. Now, another reason why I'm bringing up this again, I noticed that some students they are not applying the prerequisite knowledge. If you take a look at start 4051, one of the prerequisite is 3032. 3032 is regression and ANOVA. I know, so that was what qualified students to register for this course. But what I'm going to be presenting today, of course, regression is going to be part. So that is going to be like a kind of, reflection, for you. Okay, so like I want to beg again, I need everyone to listen. You pay for the service. You deserve to be served better. Direct all your concerns to me. Does that make sense? Okay. And I also, in addition to listening to this lecture, also watch the recordings. The recordings are available. Now, in the outline, if you look at the outline, I call that alias midtime 2 area of coverage. Two-way ANOVA with and without interaction. Blocking in design of experiment. Special ANOVA, which is analysis of sum of square for, when you're talking about unbalanced data. The random and mixed effect model. And cover, like I said, I'm going to give a tip on assignment 6. I want to tell you that the midterm 2 will revolve around these areas. Now, let's get started. I want to talk about two-way ANOVA now. This is like having a recap. Okay. Now, when you take a look at two-way ANOVA, it means we're having two factors. They are categorical. The response variable has to be continuous, or we call that quantitative. So for you to be able to identify question, to be two-way ANOVA, then you have two categorical factors with levels. And of course, the response variable has to be quantitative. What is a model? Take a look at what I'm displaying now. This is a model for two-way analysis of variance with interaction. At times, we may have a two-way ANOVA without interaction. We've done this in class. Take a look at that. If I were to solve a problem here, What am I testing here? If I'm assuming fixed effects for factor A and for factor B, I'm just going to use the classical method of analysis of variance. So which means I'm actually going to use ANOVA, approach. I'll be able to get, measure whether the response variable, on average, the response variable is the same across the levels of factor A and across the levels of factor B and across the level of interaction, which means I'm basically going to have three sets of hypotheses. One will be testing the left, whether on average, the response variable is the same across levels of factor A, the same across levels of factor B, the same across levels of interaction. That is what we mean by this. Now from there, we move to blocking in design of experiments. The idea of blocking in design of experiments is that I have one factor, which is categorical, and I'm also incorporating blocking effects. The blocking effect is categorical. The factor is also categorical. Okay, and this is going to look as if you are doing, you are conducting two-way ANOVA. There is no interaction. Okay, this is a model. You can see in a blocking, another name for it is RCBD, RCD, that we call randomized complete block design. When you take a look at the model, you're basically going to see alpha high plus beta J. The alpha high is the factor of main of primary of interest. The beta J is the blocking effect, but we can still call this two-way ANOVA because two factors are involved. One factor is of interest. The other factor is a blocking effect. Okay, so take a look at that. Now from there, we move to special ANOVA. Why is it called special? Because we don't have a balanced data. That's why it is called special. When we have unbalanced data, of course, using the conventional sum squared that we use for the balance is not going to yield good results. And that is the reason why we're actually going to consider another set of sum squared that we call type 2, type 3, and type 4. What do I mean by when do we use type 2? And when do we use type 3? Okay, what distinguish between type 2 sum squared and the type 3 sum squared is when interaction is involved or not. Okay, and as for type 4, we use that in a case of a missing data, but in this course we don't need that. Okay, so that is what we do on that special ANOVA. Okay, it is called special ANOVA because we're actually working with unbalanced data. Okay, of course, this is what I've been actually talking about. This type of sum square will come up when I'm talking about unbalanced data. So the type 1 sum squared is no longer going to be appropriate. So what is going to be appropriate is the type 2, type 3, type 4. Type 2 and type 3, what distinguish between them is when interaction is involved or not. And of course, type 4 is when we got a case of missing data. But we don't do that in this course. Okay, from there, I move to random. Okay, before I move to random and mixed effect model, is there any question? Go ahead. That is it. Yeah. Okay. Any other question? Like I said, you pay for the service. I know it's not easy to pay for college in the United States and in the Western world. So when you know what you pay for, it is your right to ask questions because you pay for the service. Okay, from there we move to random and mixed effect model. All what we've been discussing before this topic, before this, we've been assuming fixed. We've been assuming fixed factor. But in this particular area, we want to consider situation where some effects are going to be fixed, some will be random. And in fact, then all the effects in the model could be random. And I've walked you through what is the meaning of fixed effect? What is the meaning of random effects? For fixed effect, when the levels of factor, okay, they are not choosing at random. That is the available ones. That is the one you got. There's no any other one. There's no any other levels. Then we're going to call that fixed effect. For random effect, then it means we got a lot of levels of a particular factor, but we only choose some randomly. Choosing levels randomly make it a random effect. If I don't mention the method of selecting levels and another way to identify whether you are working with a random model is when a question is talking about testing variability. Variability. Whenever a question tests variability, then it's a random effect. It's assuming a random effect. Because in fixed effect, we are testing on whether on average, the response is the same across levels of factor. But in a random effect, that is not our focus. The random effect is to test the variability, whether variability between levels of factor is significant or not. I'm going to say that again. The idea, the intention, testing for fixed effects, testing for random effects, we don't have the same intention. For fixed effects, you are focusing on equality of the means across the levels of factor. But for random effects, that is not what you are pursuing. You are pursuing whether the variability among the levels of factors is significant. And that is why the test with random effects would be a test on variance. Another name for random effect model is called variance model, because our intention is on the variance. Okay, now take a look at that. I can have one way ANOVA that is a random effect. Then in that situation, assumptions we now require that the random effect should also follow normal distribution. That assumption is not required for fixed. In the fixed effect, the only term that follow normal distribution is the error. But in the random effect, the error will follow normal distribution. Then the factor, the random factor, we also follow normal distribution. Because you know why? For something to be random, it means it varies. And when something varies, we can look at the probability distribution. Because probability thrives in variation. If there's no variation, there's no probability. Okay. When you use the classical approach to estimate a factor or a random factor, you're basically going to equate, you're going to solve equation where you're going to equate the expected mean squared to the mean squared, and in a way you estimate your variance. Then you're going to have opportunity to test the significance of the variance. That's exactly what I'm talking about here. Okay, now if you're talking about two-way ANOVA now with interaction, and factor A is random, factor B is random, okay, and the interaction as well is random, then it means I'm actually having a random effect model. In that situation, if I want to use a classical approach, of course, I must be ready to apply my knowledge of algebra. In that situation, I'm also going to equate the expected mean squared to the mean square of the factor after running the ANOVA using the classical method. When you do that, you need to find what is your sigma square A? What is the sigma square B? What is the sigma square AB? You're actually going to get three variances. Why do you want to get three variances? Because you want to do this guy. You want to test for the significance of the variance. I told you in a random effect model, we are not comparing means. We only compare means in a fixed effect model. But in a random effect model, we investigate variability. We're not interested in comparing means. If you take a look at the HO, some of you have asked me a lot of questions. Of course, I can test effect of variance in the random effect model using the classical approach. How? Of course, you solve equation to get the variances. When you solve equation to get the variances, the next thing is to get this guy here that I'm showing on the board. This is in lecture, I think with 7, lecture 2 or 3. This that I just recopied them. Do you know if I want to test the variability for interaction, where the H naught is going to be 0, alternative greater than 0? Some people have asked me this question before. Why not less than 0 or not equal to 0? Can somebody give me a response for extra credits? Why is it that I'm only testing variability greater than 0? Why am I not testing less than 0? Why am I not testing not equal to 0? Can somebody tell me? Go ahead. Good job. That is a perfect response. Because if we don't expect the variance to be negative. If I'm testing, so send me a message for extra credit. If I'm testing that the variability is not equal to 0, I'm automatically testing that it's greater than 0. Because less than 0 does not make sense. If I want to take a decision regarding all this, you know what I'm going to do? I only need to get p-value. Give me 1 second. I think I have a shot. I don't know what the person mean. He said, I'm assuming you are saying absolute value of variability. Can you talk? The person online. I saw your charts. So what do you mean? So that I can clarify that. Can the person online hear me? Oh, do you mean, oh, okay. So which means it can be negative. So which means you subscribe to what I just said now, right? You subscribe to that? Oh, okay, thank you. Okay, so if I want to get a p-value here, I'm just going to write a code. Of course, you know how to get a p-value from a test statistic, which I'm going to write on the board now. Am I using a new method? I'm not. You know, this has been in your notes, right? Since this is what you're going to write in our PF into that ratio, MSAB divided by MS error. Of course, this is going to be F statistic value. Okay. Then you're going to have the 2 degree of freedom. Look at that, it's specified. A minus 1 times B minus 1. Okay. So the first degree of freedom is A minus 1 times B minus 1, comma. Then another degree of freedom is AB. This degree of freedom is the degree of freedom for the treatment. This is the degree of freedom for the error. Okay. And you're basically going to have a lower dot tail, lower dot tail. Okay. So the lower dot tail equal to false. Why do you say that? Why do you say equal to false? That is corresponding to what she said. Because lower, oh, I'm not pursuing less than. Therefore, it's false. I'm only considering greater than. Do you know for each of these, you will get a p-value. And you will be able to take a decision on each of the hypotheses, even without using the restricted method of maximum likelihood. You know, this has been in your notes. Okay. Please watch out. If you now, another approach is now the approach of the restricted maximum likelihood. This very approach will require the use of, loading 2 packages. The first one, LME4. The LME4 is to enable you to estimate the variances, which means the LME4 will save you from tedious algebraic task. When you actually use a classical approach, if you want to estimate the variance, you will actually apply mathematical knowledge, right? So the LME4 we come with the estimate of the variance. But the LME4 will not come with the p-value associated with the variance. Therefore, you need another package that we call the RLRC. Now, you're going to use exact RLT function. And I remember I said the other time, when you are working, if in your model, you have one random effect, it's just going to be exact RLT on that very, on the model. Then you're going to get a p-value. The p-value you're going to generate, that will be the p-value to test the variability within the level of that factor. But what if in a situation where you got 2 random effects? I remember an example that we work on in class. Example of sample and lab. Lab was random. Sample was random. The interaction was random. If you want to use exact ROLT, if you want to test, for instance, random effects of lab, if you want to test the random effect of lab, inside your exact ROLT function, oh my God, there are going to be three modules. The first module, okay, is the module with only lab. The second module, the one in the middle, will be the full module that have the lab and other effects. And the third module, oh my God, will be a module without lab. Okay, from this, I move to ANOVA. What is the idea behind ANOVA? The ANOVA is an extension of the analysis of variance. It means in addition to the categorical factor, I also have a quantitative factor. The quantitative factor is actually called covariate. Does that make sense now? And this is where the knowledge of linear regression is required, because we're basically going to combine the technique of analysis of variance and regression analysis. Okay, take a look at this model. In the model, this is more or less like I have one categorical factor, and I have another factor that is quantitative. I gave the example in class. If you are working with analysis of covariance, there are two assumptions. In addition to the assumptions of analysis of variance, I'm going to say that again. If you are working with ANOVA, that I call analysis of covariance, I'm actually going to have a lot of assumptions, which means we're going to retain the assumptions of ANOVA. Then with the new two assumptions added, what are these two assumptions added? Number one, there must not be relationship between treatment. When I say treatment, I mean the categorical factor and the quantitative factor. They must not have relationship. And how do I know? How am I going to test that? Then I'm going to test for the interaction between the two. If the interaction, let's say if the p-value associated with the interaction is greater than 0.05, I will start celebrating. What am I celebrating? I'm celebrating the fact that the interaction is not significant, because when interaction is not significant, then no relationship exists, which is what is required. Another assumption that needs to be tested is what is the connection, or what is the relationship between the response variable and the covariate. Because the only way I can tolerate or justify the inclusion of the covariate in my model is when it contributes significantly to the response. I cannot do that without using linear regression. And that is what, take a look at what you see, let me see if I put it here. Of course, we've done that before. Okay, let me see. Oh, okay, it's not here. There was one example we did where the diameter was the covariate and the strength was the response. Of course, we're actually going to conduct a linear regression between the response and the diameter, and the p-value have to be significant. If when the p-value is significant, then I can justify including that covariates in my model. Okay. Now, if you take a look at what I'm showing you now, this is like looking at the effect of machine, which is categorical, on the strength, on the response. But we believe that this result cannot be trusted because of what? Because we have not controlled or we have not adjusted covariate. We have not, if I'm looking at the effect of machine on the strength, and if there exists another potential variable that could also influence the response, and if it is missing in my model, then that model will mislead. In statistical analysis, if an important variable is missing in your model, then your model will be deficient. Your model cannot be trusted. What is the penalty? The penalty is that it will induce bias. It will induce bias, which is the worst enemy of us in scientific community. Okay. Now, this is what I was saying the other time. Try to look at the relationship between the response variable and the covariate. Okay. I got no choice. I will use linear regression, LM. That's how you see that. Okay. And in the end, then I will now, do what I'm supposed to do, which means in analysis of variance, ANOVA, we actually use both ANOVA. That's why at times you see LM. If you look at the summary, what do you see? Summary into module.2, ANOVA into module.2. The LM aspect will enable you to make a prediction. That is a linear regression aspect. The ANOVA aspect is not for prediction. The ANOVA aspect is only going to enable you to compare average, between the class, between the levels of factor. While regression aspects will enable prediction to be made. Because of that, I'm actually going to go into the assignment now. The tip on assignment 6. I want to tell you, if you listen now, you don't need anybody to compute to help you with that assignment. I want you to listen now. Now let's start. Let's get started. Question number 1 in the assignments. You can see what I have now. It said, they want to investigate whether age, gender, or age by gender interaction, okay, affect the cash sales offer. Now, if you take a look at question number 1, it says analyze the data to determine if age, gender, and maybe their interaction are important predictors of cash offer. Report your conclusion. This is testing. When I look at, give me 1 second. When I look at the data, take a look at the data architecture, because before I will be able to know the design, the technique of statistics that I'm actually going to use, that depends on the data architecture. I need to see the data. This is the data. Oh my God. Age is categorical. Gender is categorical. Offer say, you can see the offer says, offer and the sales volume. Looking at this now, if you take a look at what they say in question number 1, That is more or less like a two-way analysis of variance with interaction. Why do I say two-way analysis of variance with interaction? Because factor A is categorical, factor B is categorical. Right now, they are not talking about covariate. I know there's a covariate in the data, but they're not talking about that. And that is why if answering, obeying instruction, okay, is very, very crucial in passing exam. So question number one, you're going to use two-way analysis of variance with interaction. And that is the ANOVA aspect. If I want to make a prediction, I will only use LM instead of ANOVA. Does that make sense? I'm still going to write the same code, except that in ANOVA is going to be AOV or ANOVA into that, just like what I showed you before. Okay. Now, number two, state your final module from a part in a regression format. Oh my God. To state something in a regression format this is what it's asking you. I'm going to go back now. It's asking you something like this. Look at this result. I've used LM. You're going to have an estimate, the standard error, t value, P of t. This is a regression format. This is not an ANOVA format. This is like doing, this is like in a multiple, like in your 3032, which is a prerequisite to discuss. It's like we are working with you are working with multiple linear regression with two explanatory variables, and the two explanatory variables are categorical, and you are also testing the effect of the interaction. That is what it means. Because it is a linear regression module that you can use to make a prediction. ANOVA module can be used to make a prediction. ANOVA module is only going to compare means if it is fixed effect. Okay, that is what they are trying to tell you. I'm going to move so fast because of time. So state your final module. When they say final module now, what they mean, oh my God, looking at the output, you're basically going to write a fitted regression equation. Now, the fitted regression equation is more or less going to be y equal beta naught cap plus beta 1 x1 beta 2 x2, then beta 3 x1 x2. This is what we mean. Okay, where do you get all this one? Those are the estimates in your regression output. What do we use this to do? You use it to make a prediction. Okay, now what type of experimental design? I'm not going to say it. You already know. I've told you. 4, create a plot of the observed data. I'm going to show you the overlay. Okay. Now, if you take a look at question 5, use your final module to predict. Oh my God. He said to predict the average cash offer for a dealer with 400,000. Now, this is where the covariate is going to come in. It means in addition to what I have, it means in addition to the two categorical factor, I also have beta 4, x4, and this, oh, sorry, this is, yeah, x1, x2, beta, I've not used, okay, x3 now, x1, x2, okay, if I'm taking this one to be like x3, let me say x4. So this is the covariate now. Do you see that? This is the covariate now. You can run this one using the linear regression. You can also run it using the ANOVA. When you run this using the ANOVA, that is ANCOVA. And you can now, how are you now going to answer question 5? Question 5 is asking you to make a prediction. For how many groups? 6 groups. Okay? Now, I'm going to tell you how the 6 group is emerged. This guy now, they say you should take it to be what? 400,000. You know, you're going to plug in 400,000 here, right? You already know your beta 4 when you run. Don't forget, you are using module equal LM into Y on X1, X2, X1 dot X2 plus X4. That is what you are running. The summary of that, you'll be able to get, and you put that. Now, why do they say sys groups? Okay, let's go back. They say sys groups because of this guy. It's like we have 3 levels of age, and we got 2 levels of gender. What is 3 times 2? 6. Okay. Now, if I now want to be substituting, you know, if you take a look at this guy now, let's say this is age, this is gender, right? And this is age, gender, interaction, and this is the covariate. Now, you know, if I want to make a prediction now, because question 5 said, make a prediction, I need to plug in a value for this, right? To be able to make a prediction, right? Okay, what am I going to plug? I will now give you this example for you to be able to know. I'm not going to tell you what to plug, but I know when you were making age to be a factor, and when you were making gender to be a factor, I know you're going to say maybe male should be 1 and female should be 0, right? Okay, now take a look at this. I'm going to give you one example now that I show. Now, look at this example. I'm looking at the effect of sector employees belong and the location it belongs in the United States on the salary. Do you know what you are seeing here? This is a regression output of, of the situation. We have how many sector? 2 sector, public, private. How many region in the United States? 4 region. But in the regression output, okay, for 2 levels, it's going to report 1. For 4 levels, it's going to report 3. What do you see here? That's why you see public. Okay. When you see public, what has happened? R has automatically coded public as 1 and coded private as 0. Hello, did you get that? Now, how many region are you seeing? 3 instead of 4. There's a particular region you are not seeing. That's a south. Then arrow has automatically coded south as 0. Does that make sense? Now, based on this now, if I want to write the estimated equation, I'm going to write. The only difference between this and the one you are doing, right, is that there is no interaction in this one and there is no covariate. But it's still going to be the same when I put that. Now, if I want to write this module out, you see the module? Salary on that. Do you see that, right? Now, how do you now answer question about the means that they talk about? Take a look. If I plug in 400,000 here now, right? What am I going to plug in orders? Then what I'm going to plug in orders, I'm going to tell you now. Please focus the board. Please focus the board now. This area is very, very crucial to your assignment. In your own assignment, you have gender by age. You have 3 levels of age, 2 levels of gender. You're going to have 6 groups. In the case of this example, 2 levels, private, public, that is 2 levels, multiplied by the region in the United States. How many groups am I going to have? 2 times 4 will be 8. That is why I got 8 here. Now, let me tell you the first one, public south. Maybe if I want to talk about public and south, then if you look at what I have in the, at the other hand, those are the levels of the factor that appear in my arrow output. The Midwest, the Northeast, and the West, if you go back, you're going to see those are the ones that appear in my output. And public. Do you see public? Now I said there are going to be eight combination here. 8 groups. In your assignment is going to be 6 groups. Now, if I want to consider, so which means I'm going to write one factor and repeat that for the level of the other factor. Now, how many locations do we have? 4. How many sectors do we have? 2. I will start with public, and I will write public 4 times, which is going to be public South, public Midwest, public Northeast. I will do the same for private. Private South, private Midwest, private Northeast, private West. In your own, you know what you're going to do? In under the age, I think you have young, you have what is the other? I think there's one that's is it older? Then what is the? I think there's a middle one. Let me see. Young. What is the middle one? I forgot. Oh, that's just okay. Thank you. That's a middle, right? Thank you for that. And this one here is male, female, which means I'm going to have young, male, female, young male, young female, middle male, middle female, older male, older female. How many do I have? 6. Just like this. Just like this guy here. If I want to know the first one say, consider public South. Maybe I want to determine the salary of somebody, of a worker who work in a public sector and is in the South region of the United States. It's telling me to put 0 for MW. Where is MW? Maybe MW in my model is X1. Does that make sense? So you see 0, 0, 0, another public 1. Because I'm considering public South. So the public is going to be 1. Because I'm interested in the South, I'm not interested in the other region. Other region will be 0, 0, 0. You've done this in regression. Is there anyone in this class who doesn't understand this? Because you need this in your assignment. This code is what you're going to put in the model. And when you put the 400,000, that will enable you to predict the response. Now, I believe with the question of number 5, you'll be able to answer that question now. The question now said, which means question 5, you are conducting the ANOVA because of the fact that the covariate is included. Question 6, are there statistical differences among age with respect to the average cash offer? That now depends on what you have in your ANOVA model. You know, like I said, you're going to conduct in your ANOVA, there's going to be linear regression. There's going to be ANOVA. So in the ANOVA model, see whether age is significant or not. Then what group received the largest cash offer? That now depends on, for the 6 groups, you already have their average. After doing all this, which one have the highest? Which one has the lowest? Did including the covariate reduce MSE, which means when you first conduct the the research, like if you look at question 1, you did not include covariate, you run ANOVA. Okay, you have an MSE, right? By the time you now get to question 5, where you included covariate, you're also going to have MSE. Then they want you to compare the 2 MSE. MSE without covariate and MSE with the covariate. Let me tell you this. If the covariate is significant, the MSE for the one with the covariate will be smaller than the MSE without covariate. Of course, the other one is. And in the second problem, it's basically going to be, you're going to use linear regression too. If you take a look at this is like testing your knowledge of 3032. Why? Because in ANOVA, the knowledge of regression, I think I made a suggestion here for those of you who have been asking me, how am I going to get the graph, the overlay? If you follow this, you're going to be fine. Just, interaction dot plot, put the name of your data, then the factor A, you are considering age, age, gender, and the interaction, right? So if you follow this code, you will have your graph. You will have your graph. Okay. So this is another example on how to plot two quantitative variables, putting into consideration the qualitative. That is the end of that. Like I said, you need this guy here in question, let me see. Question 4. Look at question 4. Create a plot of the observed data for cash offer and sales volume. Overlay. It's just like plot two quantitative, then overlay them with the two categorical factors. And if you follow this code, but you need to load the library lattice. What is going to be factor A? Your factor A may be age. Your factor B is gender. Of course, you know your response. You put your response. Data name, what is the name of your data? You're going to see the plot. Very easy. This is where I'm going to stop today. Oh, it's another Friday, right? Sorry for taking your time. I think 1 minute ahead of. Okay, make sure you stay safe and have a lovely weekend. Bye for now, everyone.